So good afternoon everyone, and I must thank the organizer for giving me the opportunity to present my work here. Oh, I'm sorry. Yeah, so I will talk about information retrieval from black holes and some related aspects. So I will start with a brief outline of my talk. So to start with, I will give some importance of null surfaces, in particular in connection with gravity and thermodynamic connection, which Professor Padmanabhan has already elaborated. Then I will go on to discuss quantum field theory in curved spacetime with null surfaces, which in turn incorporates black holes. And then I will discuss the information loss paradox to some extent. Thirdly, how the effect of non-vacuum states can be taken into account and some possibility of information retrieval. And finally, if time permits, I will talk about quantum correlations and thermal ambience even for geodesic observers. So let us start with symmetry and Noether current. So from very basic perspective. So given the standard differential geometric structure of gravity, it's possible to construct a conserved current which originates from the diffeomorphism invariance of the gravitational action, and it turns out that it is a very simple structure. So essentially what you have is a current which is JAB, which is essentially called the Noether potential. So is this particular antisymmetric combination given this vector field VA, which is the diffeomorphism vector field. And what you do, you take one more derivative of this quantity and get a particular current. Now since this is antisymmetric, it is easy to prove that if you take one more derivative of this quantity, it is going to vanish. So J is essentially a current whose divergence vanishes, so it's a conserved current. And this is what we call as the Noether current in our theory. Now we want to understand what this J stands for, and for that what we do, we essentially project this current J along the various null directions. So essentially I have a null surface and it has normal vector to it. So this LA will stand for my null normal, and then there is another vector KB which I mentioned as the auxiliary null vector, which is also null, but such that L dot K is equal to -1. And finally there is another set of vector ECA which is essentially determines the theta phi direction on the null surface, and the inner product of this E with both of them are 0. So I just want to compute various projections of this current JA sitting here with these 3 vectors or these 4 vectors and see what they give. So the first one, I'm sorry, there is, yeah. So the first one corresponds to taking the JA vector and contracting with this EA, that's the angular part of the quantity, and that essentially can be written in a very nice form. As you can see, the first part would depend on the matter energy momentum tensor. So this corresponds to the sort of force term here. Then this omega, which is essentially defined here, is related to the momentum, and that's the Lie derivative. So this can be thought of as a convective derivative of the momentum. The sigma is essentially determined or defined in terms of the expansion parameter and the second fundamental form of the null surface, and this is essentially the shear tensor which is sitting here. Finally, this is like derivative of the pressure term, and this is derivative of divergence of the vector field V. So this is nothing but just like the Navier-Stokes equation, which we already wrote in the context of hydrodynamics, and Professor Damour was first to point this out, so by his name it goes as Damour-Navier-Stokes equation. But I should mention that original derivations were only for the case of black hole horizons, but this was for the case of a generic null surface. So given any null surface, which of course includes black hole horizon, this result should be applicable. The second one corresponds to a thermodynamic identity. So here what you do, essentially take the projection along LA, which would essentially mean taking Kj of xi. And that relation can again be casted in a very nice form. So there would be a term which is TAB xi A KB, which would be related to the pressure of the fluid or the matter energy momentum tensor. Then you have a term which is d2x d lambda root q, which will correspond to the change in volume of the null surface. Then there is another term which is kappa over 2 pi, which is related to the temperature of the null surface. And finally I have a term which is root q over 4 d2x, which is the change in entropy. And the last term is related to the Euler characteristics of the surface, and that in some sense is related to the energy. So to precisely say, to concisely say, this relation essentially says that PdV is equal to TdS minus d, which we all know is in a natural thermodynamic language. Now let us go to the final part of this equation, which corresponds to the other remaining component, that is taking Laj of xi. In this case, it turns out that this quantity Laj of xi, if you integrate over the null surface with proper volume measure, then it essentially turns out to be a surface integral. So you have a d2x, and it has 2 parts. One is kappa over 2 pi, and the other one is root q over 4. Now kappa over 2 pi, as I just mentioned, is essentially the temperature, and root q over 4 corresponds to the entropy density. So you can say that the total heat content or the total heat content of the null surface at the two horizons at lambda equal to lambda 1 and lambda 2 is this quantity. The difference between them is essentially related to the total null Noether charge associated with the surface. This is another result that I would like to mention. So therefore, finally, the take-home message from this is that earlier all these three results were known in some other form, maybe in the context of black hole mechanics, but not in the context of general null surface. So it turns out that all of them are essentially tied together in a single loop. So what you need is a single object, the Noether current, and when you project the Noether current along the null directions, what you end up getting are all the three relations that people had knew earlier. And so therefore, this seemingly giving you an unified thermodynamic description. So after giving this preliminary discussion on why null surfaces are important in connection to the gravity thermodynamic connection, I will now go to the context of black holes. So in the context of black holes, suppose I have a massive star and it's so massive that as it collapses, neither the degeneracy pressure of the electron nor the degeneracy pressure of the proton neutron plasma is able to balance it. Then you essentially have a black hole, and in that context you have a particular null surface as well, which is the R equal to 2m if you consider Schwarzschild black hole. Now as soon as a black hole is formed, there is no information about the initial state that stays there. It only depends three information, that's the mass of the black hole, the charge of the black hole, and possible rotation parameter or angular momentum. So that's how the no-hair theorem for black holes comes about. And it essentially is a one-way membrane, so you can throw things inside, but nothing comes out. So that's essentially the way the null surface comes in. So I'll briefly describe the Penrose diagram or the space-time diagram for this particular case. So essentially what you have is this particular region, which is here, is essentially a star which is collapsing and forming a black hole. This curvy line here, which is red, represents the singularity. This particular line corresponds to future null infinity. This corresponds to past null infinity. The dotted line is essentially the event horizon, and you can see if someone starts from a region here, it will essentially go reflect and can reach that point. So he can avoid singularity. But if you start from here, it will essentially go and it will grab into the singularity. So therefore, you cannot avoid singularity in this context. Now what is the paradox? The paradox is like, suppose I throw a cup of tea or coffee, whichever you prefer, into black holes. So what it will do for me, it will just change the mass of the black hole. But now suppose I go inside the event horizon and suppose I know quantum gravity, then I could essentially resolve the singularity and recover what I have thrown inside. But the problem is the black hole radiates, and it radiates thermally. So therefore, after some time, maybe it's a long time, but the black hole would not remain there, and therefore what you will have is only a single information, that's the temperature of the black hole. And Professor Padmanabhan already mentioned this temperature is related to surface gravity, and for Schwarzschild black hole, if I take, it's only related to the mass of the black hole. So therefore, all the information that you had about the cup of coffee is lost. To put it in perspective, so suppose I have some two observers here, the green one and the red one. They are measuring some temperature, so they will only see thermal spectrum after the black hole has evaporated. So now suppose someone asks, well, can there be a very small object where the black hole was there? So yes, in principle there can be, and if you go, you will essentially see there is a Planck size remnant sitting there where maybe quantum gravity is operational. But the problem is the total amount of information that was encoded into a solar mass or maybe a billion solar mass black hole cannot be contained into that small amount of quantum gravity dominated object. So the question is, what does that information went? So to study that, I will consider a very simple case, which is that of a massless scalar quantum field living in some background, which in this case of course would be the black hole background, and that is described adequately using classical dynamics, that is classical equations of motion. And as usual, we will expand the scalar field into Fourier basis. So essentially, I have a creation and annihilation operators, and this D3k stands for the k space from X to K space. So in flat Minkowski space-time, this UK which is standing there, they would have been just plane waves. But since I am now doing it in a curved background, they will no longer be plane waves. There will be some complicated functions. So the version that I will be interested in the following. So suppose I throw some particle into the black hole or something that will have some characteristic behavior, and after getting the spectrum, that is the thermal spectrum or correction to the thermal, I would like to get back that function or whatever I have thrown into a black hole. So for that context, there is two quantities which would be extremely important to us. These are the alpha and beta, the Bogolubov coefficient. These essentially appear because for Schwarzschild space-time, the vacuum state before collapse of the black hole and the vacuum state after collapse of the black hole are distinct. So therefore, there is some distinct departure. So there, if initially I started with some positive energy mode, you will get negative energy modes at the end after the collapse. Therefore, there would be some mixing, and that mixing is essentially contained in these two coefficients. In the normal situation, this alpha would have been Kronecker delta, and this beta would have been 0. So essentially, this non-zero value of beta contains the information that something has happened to the particular space-time. So essentially, what I will do, I will throw a particle, now not of course a classical particle, but a quantum particle. So I will try to explain that quantum particle by a one particle state. So this is my psi in, and this function f omega is at my hand. So essentially, all the information about the particular particle is in that function f omega. So the idea is, given the thermal spectrum that I have, can I construct or can I recover this function f of omega from that particular situation? So for that, normally what we do, normally we had a vacuum state and we construct a number operator. And the number operator would consist of when omega 1 is equal to omega 2, so we have b dagger and b. Now what are b? So initially I mentioned that phi is expanded in the a and a dagger. Now since the vacuum is not invariant, so if you can expand the field in a different set of mode functions after the black hole has collapsed or the black hole has formed. So for that case, you have two other sets of mode functions as well as other sets of creation and annihilation operators. These are this b and b dagger sitting here. So here what we do is that we essentially compute the same thing but with two different frequencies. So in normal situation, this would have been absent because omega 1 equal to omega 2 would only give you the result. But here, for the sake of simplicity or for the sake of completeness, I consider when omega 1 is not equal to omega 2. Now what you do, you compute the expectation value. What you do in normal Hawking scenario, in normal case what you do, you would have put a vacuum here, and this would have been omega 1 equal to omega 2, and that will essentially give you the natural thermal spectrum that you get. But here you will have some factors a and some b depending on these two frequencies, and they will certainly differ from being thermal. And this a and b, these functions will depend on the original function f of omega that I had written, and it can be written in terms of these gamma functions, and you can see this f sitting here, which is nothing but the Fourier transform of the original f of omega that I had written. Now with this, you can try to construct a derived quantity. The reason I wanted to do this derived quantity, because from this it would be much clear how do I recover the information about the f omega. So what I did, I had this n omega 1 omega 2, and I take a time derivative of this and subtract it by I by omega 1 minus omega 2. This is the quantity I want to observe. Suppose I have a black hole, the black hole has collapsed, and I have some radiation coming out of it, so I am an observer at late times. So essentially I can compute this quantity n omega 1 omega 2, that is the correlation between two different frequencies and how many particles I am getting, figuratively speaking, and I am taking time derivative of it. I am taking this particular omega 1 minus omega 2 division. And ultimately from this, if I can get this function f of omega by kappa, I can make this particular Fourier transform, and that will essentially give me that function f of omega. So then what you do, suppose you start with a real initial state, because that's what will give me the full information, then essentially the Fourier transform will satisfy some relation like that, that is f of capital omega by kappa should be f star of minus omega by kappa. And then if you compute this quantity s, so I earlier mentioned that this quantity d was there, if you recall, this d constructed out of n, and then what you do, this d is exactly sitting here, and you consider this particular combination, so which is nothing but f omega 1 by kappa and f star omega 2 by kappa. Now since you have access to all the omega 1 and omega 2 modes, therefore from this particular s value, you can essentially compute what is f omega 1 by kappa. And since you know f omega 1 by kappa, you can plug that in into this equation, and you can get the solution for f omega. So in that way, you will know what you have thrown into the black hole by analyzing the spectrum, and in particular the non-thermal corrections to the Hawking radiation. But there are some assumptions involved, so I will just try to mention about this. So therefore, the knowledge about the corrections to n omega 1 omega 2 will enable us to compute this function f omega by k, and it requires some symmetry. That's the real initial state which we have assumed. So what can be future outlook? So we have only used 2-point correlation functions, if you recall, but more information can be retrieved possibly by looking at higher order correlations of the theory. And this, in these cases, we may not have to assume that the initial state has to be real or something in order to retrieve the information about f of omega. So this was about the black hole thing. Now let me go to a peculiar case for a particular black hole, which is called the CGHS black hole. So let me explain this a little bit. So this essentially occurs in two-dimensional dilatonic gravity, And in that case, what we have is this is again a Penrose diagram. So this full thing is their full space-time. There are essentially 4 halves. This is the right half, so you can see this R symbol here, and this is the left half, so you can see this L symbol here, right? Now this particular green line corresponds to, thanks. So this particular green line corresponds to a null shell which is collapsing and forming a black hole. It collapses and hence the singularity is formed, and this is the event horizon which is generated. Now interestingly, this particular region which is here, this triangular or weird shaped region, essentially is the black hole region, so the curvatures are non-trivial, but this particular region is essentially flat. There is no curvature in that particular region. Now I can construct 2 observers. One observer who starts from here and goes to this position, another observer starts from the same location but goes to this IL plus. Now this observer will of course go through curvature effects and things like that, so he will see the normal Hawking effect. But the question is, what will happen to the observer who is moving to the left? He is always moving in the flat space-time because there is no gravity in that region, but he cannot actually access anything in this particular region because of this null shell collapsing. So as a consequence, you will have some bizarre result here, that is, the left moving observer will see the space-time to be free of curvature effects, but since a portion of the null hypersurface which I just showed, this chi r minus, is essentially inaccessible to this observer, what will happen is that he will see there is non-trivial Bogoliubov coefficients. So I mentioned these coefficients alpha and beta. If they are Kronecker delta and 0, then things are fine, but he will see these are not delta, Kronecker delta and 0. There would be some non-trivial value. And as a result, this inertial observer to the left, who is moving in flat space-time, will essentially observe Unruh effect. And that's a very peculiarity of this 2-dimensional CGHS space-time, and we actually do not know of any other example of space-time where this happens. But in particular, it seems that it is possible that even in flat space-time, moving observer, it is inertial observer, can see Unruh effect. So with this, I must summarize. So first of all, importance of Noether current and null surfaces in the gravity thermodynamics connection have been presented. So I can write down various interesting thermodynamic identities giving the Noether current, and of course we must have null surfaces in that. And secondly, this does not only hold for black hole horizons. I mean, of course it holds for black hole horizon, but it holds for a much more broader class of null surfaces like Rindler horizon, time dependent horizons and so on. So even when a black hole eats up matter and its horizon increases, even in those situations these results are applicable, because all the kappa, alpha, beta, all the coefficients, mu, ab, all the 2-dimensional metric that I have shown, they are all dependent on time. So this is applicable in time dependent situations as well. Finally, treating the matter field as fundamentally quantum, and by studying non-vacuum distortions, because the expectation values of the number operator were taken for non-vacuum states, we can actually get or derive the information about the initial state. The diagonal elements, that is I took n omega 1, omega 2, if omega 1 is equal to omega 2, they will lead to complete information only in case of real and symmetric distributions. But if I have real distribution and I consider off diagonal elements, then also I can get the full information. And finally, the left moving inertial observers in CGHS space-time will observe Unruh effect. So with this, I must thank all of you for your attention. So thank you.